All right, so this video is going to directly tie into the second, if I'm not mistaken, tech assignment, the one that you're actually going to work on today. So there's a lot of words here, and the words, oftentimes explanations are designed to simplify a process rather than make it more complicated. But this is one of those things where I feel like it makes it more challenging if you lead off with the textbook definition. But if you get into the practical application of it, I'm using the term practical here loosely, but basically a problem. Dive in a little bit before you start getting into the textbooky stuff. Then I think it starts to make a little bit more sense. So we have a population consisting of the values 1, 2, 3, and 4. All right. So population. Let me get my writing tool here. Population 1, 2, 3, and 4. All right. Vaguely defined population doesn't really come with any clarification as to what it's referencing. But that population will have a mean and a standard deviation, which we can compute. The mean will be easy enough to do by hand, but the standard deviation, even the easy problems, are still complicated. So I'm going to pop that in. 1, 2, 3, 3. Reference, Easter egg, first one to submit gets the bonus. So we have 4 values, 1, 2, 3, and 4. I'm going to quit out of there. Stat, calc, option 1. My data values are only in L1. I'm going to calculate. So we have 25, geez, I'm just making stuff up now. 2.5, and a standard deviation, population standard deviation of 1.118. All right. So that 1.118, I'm just going to hold on to that value because we're going to need that later. All right. So in my VARs menu, it's option 5 for you, but I'm going to option 2 for me. That sigma value, I'm going to store that in as, I'll just store it in as S. All right. So anytime I hit S, that value is going to come up. All right. Now what I'm going to do is come up with samples where n is equal to 2. So samples of size 2. All possible samples. All right, so if I'm selecting 2 values with replacement from the set of 1, 2, 3, and 4, I could get 1, 1, 1, 2, 1, 3, 1, 4. I'm going to leave a little space. 2, 1, 2, 2, and a little bit more space. 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4. Oops, undo, redo. And then finally 4, 1, 4, 2, 4, 3, 4, 4. My spacing wasn't as consistent as I would have liked, but there was a rationale. It just didn't play out the way I had it intended in my mind. So what we're going to do is we're going to find the average of each of these values. I'll just write AVG. Average of 1 and 1 is 1. Average of 1 and 2 is 1.5. 1 and 3 would be 2. 1 and 4 would be 2.5. 1.5. So basically the halfway point between these two numbers, each pair of numbers. All right, so continuing on, 4 plus 1 is 5, divided by 2 is 2.5. 4 plus 2 is 6, divided by 2 is 3, 3.5, and finally 4. All right, so each one of the red values is a mean. All right, so my list of means well, I could write them all again, but it would essentially be just reproducing what I have here. I can do it as a frequency table just because I have repeated values, so X bar and each corresponding frequency. So the 1 only occurs once. And I'll put a little check mark when I'm done with it. The 1.5 occurs twice. Two occurs 3 times. Oh, I boxed myself into a corner here. Meh. Let me use the tried and true technique of moving stuff. All right, so 2 occurred 3 times. .5 occurs 4 times. 3 occurs 3 times, so we have symmetry. Now that's an important characteristic here. Because, why? Because in our original distribution, each value only occurred once. So that was a uniform distribution. This one appears to be more of a normal distribution. All right, and so that actually is going to play out in the definition of the central limit theorem. All right, but for now, let's just run some numbers. Running numbers. Computation. Quote from what movie? I'll give you a hint. It was an AI. And the individual's name was an acronym. And I'm pretty sure this character didn't actually run any numbers. So 1, 2, 3, 4, 3, 2, 1. So now I'm going to stat, calc 1, L1, L2. Calculation. All right, so from here, what I'm going to get is a mean. That mean is not of the X values, but of the X bar values. And that's equal to 2.5. The sigma, also of the X bar values, is about 0.791. All right, so here you could see, hopefully, that mu is the same. I'm going to go with a lighter highlighter there. Oh, it's this one. Mu and mu sub x bar are identical. But then also you'll see, pretty interesting consequence here, that these are not the same. Like, wow. That's startling. They're not the same. All right, so what are they? Well, we have a relationship up here that tells us what they are. You know? So what it's telling me is that if I take the sigma that I got from earlier and divide it by the square root of n, then I'll get the thing that I'm looking for. All right, so sigma, which I stored in as S, 1.118. If I take that and divide it by the square root of n, so about 1.118 divided by the square root of 2, look at that, about 0.791. So this isn't a proof, but it's a justification of the central limit theorem, and that is that these two rules apply in order to really kind of streamline the process. Instead of actually coming up with every possible sample of size whatever, what I can do is take my population mean and just define that as mu sub x bar, and take my population standard deviation, divide that by the square root of n, and what I'll end up with will be the sigma sub x bar value. So none of this work would actually be required. And there it is.